Okay, this video tutorial is going to look at polymers. So what are polymers? Polymers are what we call macromolecules, or big molecules. And let's just look at the name first here. If you look at poly is a scientific or mathematical term that's used to mean many. So a polymer is made up of many units, many bits. For instance, you may have heard of a polygon as an object with many sides, with lots of sides. So poly just means many. So they're formed by joining together a large number of smaller molecules, which we often refer to as monomers. So these are single, mono meaning one, single units. So a polymer is many units, whereas a monomer is a single unit. So if maybe you've looked at DNA as a polymer of lots of nucleotides stuck together, or most of the alkanes we've looked at, you could say, as a polymer of carbon atoms kind of stuck together in a chain. So one example, what we're going to look at here is how we can use alkanes to make really long chain polymers. Alkene molecules, especially alkenes, because they've got those double bonds, can be linked together to form what we call addition polymers. So addition polymers is where we simply have a whole lot of monomers that get added together, sort of end to end, to form really long chains. And these really long chains are actually what you and I would generally refer to as plastics. So plastics, most of the plastics you see around you are long chain polymers, really long chain polymers of alkenes that have been joined together end to end. And the length of the polymer determines kind of the property of the plastic too. So longer chain polymers will be harder and have higher melting and boiling points. But that also means they're less sort of flexible or malleable, shapeable. Whereas other plastics that are sort of maybe more bendy are probably not quite as long. But in each case, plastics are actually very, very long chain polymers of usually alkenes. So let's have a look at that. How can alkenes combine, or what is it about alkenes that allows them to join together? So if we look here, and I'll just pull out a pen. If we look at an alkene, so let's look at the simplest one, just because I'm pretty slow at drawing on the computer. So if we look at ethene, so this double bond, carbon, ethene, and then it's got hydrogens sticking up. Now sometimes they're drawn a little bit on an angle, and it's just to sort of space out the bonds. But I'm just going to draw them up in this case because I'm going to change it in a minute. So ethene is a double bond, carbon double bonded with each one has two hydrogens on it. And so if I take another ethene over here, so ethene is a monomer that we can use to piece together a long chain polymer. And the way that works, what happens is basically it's all about breaking open this double bond. So if we encourage, with a bit of encouragement, we can get this double bond to break open. And so instead of having a double bond here, you can imagine sort of half of this bond sort of rotating around and sticking out on this side. So just maybe a little half a bond. Alright, so that's the one electron. So remember, there's a pair of electrons in each line, and you could imagine we've got sort of here sort of a half a bond, a single electron rather than a full bond. And over here we can do the same thing with a bit of encouragement. If we break open this line, this pair of electrons that's being shared there. So remember, each individual line, each bond is actually a pair of electrons. So one electron comes on this side, and one electron comes on this side. Alright, so now we've got one electron on this side and one electron here. So these can pair up now to form, rather than this piddly little half bond, we can get a bond. And I've drawn them a little bit far apart, but we can get a full size bond forming in between these two carbons here. And so at the ends here, this isn't a full bond, it's just a single electron. But if we put another ethene molecule here, then that double bond could open up, and we'd get sort of a single electron that could pair with this one to form a bond there. So essentially it's all about, if you've got a double bond here, that can kind of open up, and we can get, rather than having a bond between these two carbons, that bond can be broken open and one electron goes to each side and is shared with a carbon from another ethene molecule. So it all gets linked together. So what does that look like? Well, so we start with lots of ethene molecules. You can see them all here. And this one is going to break open. So this double bond here, one of those bonds is going to break open and form sort of a half bond out there, and one of these is going to break open and form a half bond out there. So we'll link that together, and then over here this will break open and we'll get, you know, one electron out there and one electron there, so we'll get a bond forming between them. And so when those double bonds kind of break open, we can actually link them all together to produce polythene. So polythene goes by a few names, polythene or polyethene. So that's I guess probably the easiest one to learn, because this is really just saying it's poly. Sorry, let me go back. So it's basically many ethene molecules stuck together. So we've taken lots of ethenes, many ethenes, and just stuck them together. So these are three names for the same thing: polythene, polyethene, polyethylene. But polythene you've probably actually heard of. I think it's used sort of like a varnish or something. But anyway, you can see here, if we link these together, we end up with a long chain of carbons like this. And I've just shown, you know, a realistic size piece here, but it actually would extend much further. I couldn't fit it on the screen or it would get really tiny. We can keep adding them till we get really long molecules. So if we keep doing that, we get really long molecules, a really long polymer of ethene. So rather than draw that, we often draw it like this. We show the unit, which was ethene, so the two carbons there, without the double bond, but with the lines coming out at each side. So essentially, we've shown that this double bond has broken open and is ready to attach to the next one on that side, and attach to the next one on that side. And then we put an N, because polythene molecules can be between 2,000 and 20,000 carbon atoms long. So you don't really want to try and draw that. You know, you don't want to have to draw 2,000, let alone 20,000 of these, you know, on a page. And you don't even really want to even just do the molecular formula, you know, C2000H. So in this case, especially for trying to show the structural formula, we just show the unit. So in this case, the two carbons with that double bond is opened up, so bonding, you know, bond ready to form on either side, with an N, where the N just is the number of times it's repeated. So if we had a piece of a polythene, a polymer, a molecule that was 2,000, we could put 2,000 there. Or if we're not sure, we can just put N, and it just means it's repeated a certain number of times, we're not quite sure. And it's worth noting, though, if you have a look, though, polyethene is actually an alkane. And that's, you might be thinking, yeah, so what? But have a look at it. We do actually have the ending "ene" here, so it's a little bit of an exception when it is actually an alkane. And the reason for that is the name, it isn't actually named after the final product. It's named after the monomer, the units out of which it's made. And that's because if you go back to our prefixes, where we said like meth, eth, pro, bute, all of those prefixes, we don't actually have prefixes for things that are 2,000 or 20,000 long. So we name them based on the unit from which they were formed. So polyethene means it was made out of lots of ethene, alkene molecules, but now it's actually become an alkane. So it's worth just noting that too. And we'll go back just to make that a little bit clearer. You can see here these are all alkenes. They've got double bonds. But in this addition reaction, we're making an addition polymer, which is adding lots of units together. These double bonds break open, and that's what forms the link between them. And so that's, you can see here the product is actually an alkane. It doesn't have any double bonds. Cool, so that's basically it for polymers. So just before we leave that, it's worth just remembering a lot of the plastics that we have around us are actually just very long chain polymers of alkenes. So they're basically just long chain alkanes. And if you think about our fuels and things, what makes them different from fuels like gasoline and petrol and methane gas and things like that is basically they've just got really, really long chain molecules. So having really long chains it means that they have much higher melting boiling points. They're always solid at room temperature. So plastics and basically virtually every plastic that you'd see around you is just a long chain polymer or a really long chain alkane that we've made by linking together. So this is kind of the opposite of cracking, really. Cracking produces the monomers, and so here it's basically then using those monomers and linking them together to make the really long chain ones. But cracking can be a really important part of actually producing. That's where we get some of these monomers, the alkenes from, and if we then separate those off, so we've just got a whole bunch of short chain alkenes, we can then link them together to make these really long molecules, which are things like plastics. Cool, I hope you found that helpful, and we'll leave that there. We'll get on with the next one.